on the internet. So if you go to the address there, just code.mlcollector.org/libsizzle. There is a free version. You can just use it as a dynamic library, and it's like a oracle for binary buffers. Is there shellcode in it or not? And that's very nice because you can just take like network info or whatever, throw it at it, and ask is there shellcode in it or not. Of course, it doesn't work for return-oriented programming approaches. It really just only detects bytecode. But for example, for CTFs or whatever, this is really nice because there you usually see real shellcode. And then if you have detected shellcode and actually you want to know what does a shellcode do, there is the free shellcode emulator written by Markus Kötter and Paul Becher, libemu, which I've been talking about before, which can also tell you what would the shellcode actually do on a real system. So you can get there for free at the other address. So let's add a little demo of that. And that's really just a side project. I mean, as soon as you have like libcpu, like a virtualization solution, you can create so many other projects from that very easily. So let's first have a look at performance. I'm piping 16 megabytes of urandom input to it. And yeah, let's do it a second time so it can cache the data from the hard disk. So it in total takes 300 milliseconds to examine 16 megabytes for data. And of course, since this was urandom data, we did not find any shellcode in there. There's some segmentation faults occurring that were not expected. I'm filtering out stuff that is inside the basic blocks, and there's some strange segmentation faults also happening, but yeah, we're catching that here. So as you can see, it's quite performant, and if I would be doing it on 2 cores and not be running my presentation, VMware, Windows Virtual Machine, I can, on my laptop, catch up with 100 Mbit line speed of data. And if you do it on a commodity server with like 4 cores with like, I don't know, i5 or whatever, you can do it at 1 or 2 gigabit line speed. So you can really do this on live network streams and stuff like this, or you can also plug it into your honeypot solutions and whatever. Well, next example is, I've been testing this with various shellcodes. Initially, I was going to test this with like Metasploit shellcodes, but these are, quite known, and so what I ended up with is testing it from last year's DEF CON shellcodes, because there people wrote their custom shellcodes with custom encoders that weren't so easy to detect. And yeah, so we're running it here on some other buffer. Of course, this is now only some PCAP data, only 200 kilobytes, so it's a lot faster. So we end up having 34 different candidate offsets in there, and then we actually at one offset found the real shellcode after verifying it in the emulation. So if you look with the disassembler, what did we actually find there? Well, there was some knobs of first, some knobs obviously, and then it's some inc EDX, sub ECX, ECX, so that's just some initialization of registers there. And then the interesting instruction is the F3 instruction you can see there. This is the floating point instruction. It's just a random floating point instruction they've been using, but this sets the instruction pointer for the FPU to that specific address. Then they initialize some loop counter there, and then there's the interesting gadget storing the floating point environment. So that's exactly what you would see in shellcode. And then what you see after it is like here they start a little loop, which would then decrypt the shellcode. So in each iteration they add 4, so they encrypt 1 double word at a time. And actually XOR here, and what looks like garbage here is actually already the XORed loop instruction. So if you do the math, if you add to this address add 15, you will end up inside this instruction, and this is the first XOR here. So yeah, that's what they do. So it worked very well on that shellcode, which was XOR encrypted shellcode, and also if you have raw shellcode, which actually, funnily, in this case, if you have unencoded shellcode, it's a little bit harder to detect because you don't have these getPC gadgets. So I had for Linux shellcode to add yet another gadget, which is the int80 gadget. Obviously, a shellcode does system calls, and that works too. So what I did was I combined the urandom data and to the end appended some other shellcode during the CDF. And again, the urandom data takes some time, but it doesn't really generate any false positives. But then we have at the offset at the end, we actually do think that we have shellcode, so let's look at that. And well, it turns out it actually is shellcode. So, oh, why is my terminal fucked up there? Okay, there we go. Actually what you see here is they just zero out the ECX register, then they give it as a last parameter to the function they call. They load EAX with the system call number 6, and then invoke int80. And well, this is obviously not a Linux shellcode, but a FreeBSD shellcode. But still, they use int80 for invoking system calls on FreeBSD too, so we detect that shellcode very easily as well. And so this is very performant, it's very easy to implement, so yeah, nothing too cool, but as I've said, it's released for free, and it's very useful for intrusion detection stuff, or if you want to write honeypots, you need that, like if you want to write low interaction honeypots. Okay, so let's get to the essence of this talk, Dirtbox, or what I call the system call implementer Sisyphus tale, because, well, yeah, initially you're like, okay, there's thousands of APIs and only 1,000 system calls, but obviously 1,000 system calls is still a lot to implement, and yeah, system calls aren't really documented in the Windows world, so it involves a lot of reverse engineering of NTDLL and NTOS kernel and stuff like this. So it's a lot of work, but still. So why system call emulation? Well, I've already told you that I mean, API emulation is kind of weak in some regards, but still it's easier to implement, so why go through all the hassle? Well, there's some documentation actually out there. There's the Wine and Reactor OS source code, so they can already give you some pointers if you would be doing this on your own. And the other reason to do the system call emulation is we get a lot of genuine execution environment that really looks like on a real Windows system for free, because we're executing all the native code that would set up this environment on a real Windows system too. And then again, with all these APIs, there's really an unbound number of APIs. So there could be just some fancy DLL, and then you again have to add these API calls and so on. Whereas with system call numbers, you have well, it's quite a high limit, 1,000 system calls, but it's a fixed limit. And you know, if you would implement all of these, then you're definitely done. Instead, with API level emulation, you know, it's like this arms race you always see with malware. And that's the issue that, as I've said before, some malware directly issues system calls, like some viruses mostly, not the Trojans and Vectors you see, but all these really cool metamorphic viruses, they often use system calls directly. And we support that out of the box because that's what we do anyway. And we avoid all these API side effect detectability issues entirely. So I've been saying we get things for free. Well, what actually do we get things for free? I have 3 examples. There's more stuff we get for free, but just picking out 3 examples. We get PE parsing for free. If you have been doing some PE stuff, you will probably have noticed the PE format is very nicely documented by Microsoft. The only issue with the documentation is that it's not accurate in that sense that the Windows binary, the Windows PE loader behaves differently than this documentation. And also the PE format, it has some things where it's very easy to screw up. So if you do PE format fuzzing, you can find a lot of interesting bugs in like IDA and other software. So there's not easy to parse PE, even if a lot of tools support it. If you really dig into the file format and try to break some stuff, you can break a lot of tools very easily. But why do we get it for free on the Windows platform? So the process startup if you create a new process on the Windows in the Windows, it's mostly handled by the new process and not by the kernel. So on Linux, for example, loading the binary is entirely done in the kernel, mapping everything. But in the Windows world, it's mostly done in userland, which was a surprise for me, at least when I looked at this the first time. So the step by step, it goes like you have always a process that tries to create a second process, unless we first process in the system, but we're not doing booting anyway. So you will have a process calling the nt-create process system call, which allocates a new system, a new process in the structure in the kernel. And then the creating process will create a so-called section object inside the just created process, which means it basically maps the image and also NTDLL into the new process. So this is what the kernel has to do. It requires that the kernel parses the section headers of these 2 PE files. But parsing section headers is not so difficult. There's way more difficult stuff in the PE format. So we just need to map the different sections into memory. And then the creating process will create a new thread with the on the entry point, with the entry point pointing to a place inside NTDLL. So it does that with an asynchronous procedure call. And this specific execution point inside NTDLL is called loader initialized func, the name already says, it's the initialization of the process. So this point in NTDLL would do the relocation of the image if necessary, resolving the imports, invoking the thread local storage callbacks, which are often used by malware for obfuscation, invoking DLL startup routines if it's a DLL, and so on. It will automatically do this for you, and we'll do some more magic, which I will show in the demo. So all this, more difficult parsing of the PE format is done by the NTDLL bytecode, and we don't have to implement that our own. So all we have to do is implement NT-create section and NT-map view of section for these seg image sections. So it's really only parsing section headers. So there's already a lot of stuff we got for free, and well, if there's actually PE bugs inside there, then it wouldn't really run on the real Windows system, so we get a very genuine view of binaries. Whereas a lot of malware analysis tools and disassemblers and so on, sometimes they don't support stuff that would have worked on Windows, and sometimes they allow you to do stuff which actually wasn't allowed on real Windows systems. And there's really nice stuff you can do, which goes beyond the scope of this, but yeah. So second thing we get for free is a very accurate heap implementation. Because of API level emulation of these antivirus emulators, a lot of them have their own guest heap allocator, and they implement this in the emulator host. So because they're doing the heap implementation in the host, what you will see is that if you call malloc or RTL allocates heap or whatever, heap alloc, it will give you some address because, of course, they need to provide your memory management. But and on a real-world scenario, you do have like heap headers in front of these addresses, and most of these AVN emulators won't put these heap headers there, for example. Then again, on a real Windows system heap, you will have stuff like arena structures for heap and so on. And a lot of antivirus, some put heap headers there, some like fake heap headers, but these arena structure stuff like this, that is not put there by any antivirus emulator I've known. So it's very easy to, by looking at the heap, figure out that it's actually an antivirus emulator you're running in. Luckily for us, the Windows heap is implemented in NTDLL2. So all the memory management is done in user mode as well, as we would expect probably. And all it does is interfacing the kernel with NT-virtual-alloc, NT-virtual-free, and so on. And these are page granular, so we don't have to do any heap blocks or whatever. We just care about allocating pages and freeing pages. And yeah, stuff like heap protections, like heap cookies and so on, are all handled in NTDLL. So we got again a very genuine environment in that regard. So if you just want to fingerprint emulators, just do a malloc of 0 byte size and look 8 bytes in front of that, and that will usually always already tell you you're running inside an NV emulator. Other issue would be if you want to have more advanced detection, deliberately overflow your own heap block, overriding the heap cookie, and if you're free, the C block, see if there's an exception generated or not. And if there's no exception, then you're probably inside an AV emulator. And the third thing we get for free is proper structured exception handling. Structured exception handling means that you have on the stack a linked list of exception handlers that are function pointers, basically, that will handle exceptions. And all we have to do is actually provide a context record, which is just basically a view of the current CPU state. So it's very easy to generate the contents of the structure for us. And then jump to inside the guest, of course, and TDL-KI user exception dispatcher. So that is what the real kernel would do as well. And all of this handling of structured exception handling will be done by NTDLL for us again. So it will look up the current top of the SEH chain in the thread environment block, walk this list, invoking these exception handlers with the correct flags, and especially invoking them twice, because you'll always have one run finding an exception handler that can handle the exception, and then there will be an unwinding run where these functions will be called a second time with different flags. And a lot of AV emulators, they don't do the unwinding run, so if your function pointer gets only called once, you can detect this, you can look at the flags and so on. And also, actually, NTDLL, depending on the Windows version, of course, will check for safe SEH structures in your binary. So again, if you would have a safe SEH structure in your binary and then create a non-registered SEH handler on the stack, and you don't run into an exception when triggering, but instead your exception handler gets called, then again, you know you're in an antivirus emulator because they don't care about safe SEH at all. So yeah, just link your binaries with your malware with safe SEH and deliberately trigger an exception to a non-registered SEH handler, and